When you're trying to do a double integral in Cartesian coordinates, you want to find something like the area. And a little bit of area is actually going to be a little bit of x times a little bit of y. You start at point xy, you move over dx, you move up dy, it's a rectangle. The area of a rectangle is length times width, so dA equals dx dy, or dy dx, depending what order you want to do the integrals. In polar coordinates, we're drawing circles and lines through the origin, and so we don't actually get rectangles. If we make it small enough, though, we can get something that's shaped a lot like a rectangle. So let's figure out what the area of that is, pretending it is exactly a rectangle. So if we go out a distance r to a point r theta, and we go a little bit farther out, we go in the r direction, that adds a dr. So the length of this box is dr. The width is a little bit trickier. This angle from here to here is theta, and we're talking about moving a very small amount of additional angle, d theta. At a distance r, what is the length of that? Well, we use the geometry fact that x equals r theta to show that this length is actually r d theta, because d theta is the angle and r is how far out we are. So if you put those together, length times width giving you a little bit of area, the length here is dr, and the width here is r d theta. And we usually write it in this order just because we like to put the r with the dr. Of course, it's possible to do the integral in the other order, but this is the usual way of writing it. That's why d area is r dr d theta. Because we're imagining things getting tiny, down to infinitesimal, this is close enough to a rectangle that we can treat it as a rectangle in the limit, and it all works.